So now I'm going to invite our next speaker up, Dr. Andrew Graus, guardian of the other galaxies. And I actually don't remember your answer to the question, what would you eat for 60 days?
Well, I know I'm in taco land, but it was burritos.
Oh.
So, I'm sorry. I know, starting off on a bad note. Ugh.
So if we could get Andrew's talk up on the great, cool, thanks.
We can just riff
wing
for a
it.
little bit.
Do you wanna? That's cool. I was gonna say you could wing it. I don't know if you want to do that at all. Dark matter.
Well, I could start by asking. So I'm going to talk about dark matter. So I wanted to know, like, from the audience, maybe a show of hands, how many people know what dark matter is? You know, raise your hand. Anyone?
Cool.
Anyone? We got a couple of tentative hands.
Yeah.
Okay. Thank God, because we've been trying to find that damn thing for like 30 years. So if you could, yeah. That was my joke. That was the only joke.
All right, give it up for Dr. Andrew Graus.
Okay. Thank you. Thanks for having me. And thanks to the hosts and everybody here. And Danny for that great talk. My favorite moon is Europa, actually. But I'm really striking out here, aren't I? Okay, but I'm going to talk about the search for dark matter. And so I'm going to start with a brief thing about the history of dark matter. So to start, I'm going to talk about sort of the initial observations that indicated that there might be something like dark matter out there in space. And so the story starts, for observational evidence at least, it starts with this guy, this charming fellow here, Fritz Zwicky. And so what in the 1930s, and what he did was he studied galaxy clusters. So this is a cluster of galaxies here. And what he was looking at was he was trying to measure the mass of this cluster in two different ways. And so there are two ways you can do this. One, you can measure basically the velocity at which the galaxies through this are moving through this cluster. And they're kind of all bound together by their mutual gravity. And because you can measure the velocities of individual galaxies, you can sort of answer how much mass the total cluster should have in order to keep all of those galaxies in orbit together. Right? But you can also do it another way. You could simply count up all the little galaxies in here, and we know roughly how the light in those galaxies maps to the mass in those galaxies. So you can get a mass measurement from that, and you can say, well, does all of the stuff we can see, does that explain all the mass that must be in this cluster? And when he did that, he found that the mass that you get from dynamics, from measuring the velocities, is about 500 times greater than what you would see by just measuring the light and sort of counting up the individual galaxies. And so he said, maybe this means that there's some extra dark matter, he called it dark matter, that is inside of these clusters, okay? And so there was some debate about what this means, whether or not he was crazy or, what. But the next solid observational evidence came much, much later, in basically the 60s and 70s, with people like Vera Rubin, who measured the rotation curves of disk galaxies. So here's a disk galaxy on the side. And so what she measured was the speed at which stars rotated around the center of this galaxy. And so if you were just to look at the light, most of the mass is here in the center, right? Most of the stars are there. And so what you would expect is that the stars on the outskirts are moving much, much slower than the stuff in the inner regions, or else they'd fly off the side. And so she measured the rotation curve, basically the velocity is a function of distance here. And you would expect it to fall off if all of your mass was just coming from the light there. But what she found was basically the opposite, that it just kind of flattened out. And so the conclusion that she reached, and many others, was that these galaxies must be buried in sort of this big cloud of something else that they call dark matter. And we still call it dark matter today. And so there were a lot of other, evidences from cosmology and other things like that there should be something like dark matter. But today, what do we know about dark matter? So I'm just going to say all of the things that we know about dark matter. It exists. Probably. So that we know that. If it exists, it has mass, right? Because it has to generate gravity. And also, it doesn't interact often with normal matter. So if so, we'd see it, okay? And so, interestingly, there were a lot of speculation as to what this could be. Is it planets? Is it just small, faint things, planets, comets, stuff like that? And that is disfavored. But one thing that was really enlightening came from the particle physics community. And they'd been trying to figure out problems of their own, problems that we don't care about. But it turns out that they actually designed a particle called what we call a WIMP. So a WIMP stands for a weakly interacting massive particle. Basically, it's something that's pretty large. It's about 100 times the mass of the proton. And it interacts very infrequently with normal matter. But it has mass, okay? And this was proposed as maybe an idea for what dark matter could be. And kind of the thing that pinned this to be really the most favored dark matter candidate really came from kind of what I do, which I don't do dark matter particle physics. What I do is simulations of how galaxies form. And so what I have here is a white or a blue background of nothing. But this is actually a simulation. What's here is dark matter. And so this is assuming dark matter is a WIMP. And these kind of splotches, you can see overdensities and underdensities. This is sort of to mimic what the universe looked like at the very beginning, very soon after the Big Bang. And so if I let this movie run, this is a pretty large segment of the universe. At the present day, this would contain tens of thousands to hundreds of thousands of galaxies. And as this thing evolves over time, you can see because it's just gravity that's happening at these scales, you can see it starts to form into sheets and then filaments, this sort of spider web. And then you get these kind of knots here. And these knots are dark matter halos. Basically, they're knots of dark matter. And the reason why we think this is important for galaxy formation is we think that every galaxy forms at the center of one of these dark matter halos. The citation is covered up, but this is a simulation by Benedict Dimer for reference. And so one thing that was done in the early 90s was comparing this simulation of, say, of what the universe looks like if dark matter is a WIMP, comparing this to the actual distribution of galaxies. This was first done in the 90s with the CFA survey. This is an updated version of this from SDSS, the Sloan Digital Sky Survey. And while these don't look that similar because I'm using a very high resolution simulation and this is pretty somewhat old map of galaxies, if you look at this statistically, they're indistinguishable. And this was really the thing that pinned, like, the dark matter is absolutely 100% a WIMP. Yep, definitely. There are a couple laughs. I'll get back to that in a second. And then we tried to find it. So I'm going to talk now about, so how do we actually look for this thing? If it's a WIMP, okay? I'm assuming that it's a WIMP. Maybe a bad assumption. But to use that, I'm going to use this, which is kind of a mock of a Feynman diagram, which is used in particle physics to look at particle interactions. And so what I have here is on the left, you read this thing left to right. On the left is two particles that I've labeled SM, which stands for standard model. All that means is something that we know what it is. It could be a proton, could be an electron, could be a photon, who knows? And then there's this thing in the center here, which is an interaction, which I'm just going to call particle physics stuff. So these things that we know about come together, particle physics happens, and then hopefully we get a dark matter particle out, okay? And this is actually something that we know, and probably everybody in this room knows. This is a particle collider. This is a collider experiment, right? And so what the cool thing about this diagram, and the reason why I like showing it, is that you can read this diagram any way, right? You can kind of reverse it. This is going to be cut off a little bit. But you can reverse it and say some dark matter particles come out somewhere in space. They come together. They interact. And then it produces something that we know what it is. Could be light. Could be an electron. Who knows? And then we call this indirect detection. And the final way that we try to find dark matter, or that I'm going to talk about, there are many other ways, is this reading this diagram kind of up and down. And here we get direct detection. And this is basically you take something that we know, you hit it with a dark matter particle, and the dark matter particle bumps a little bit, and we can detect that bump, okay? And then we call that direct detection. So in the last few minutes of my talk, I'm going to talk about one specific example of each. starting with collider experiments. So this might be something that most people in this room know what it is. This is the Large Hadron Collider. Well, this is France, but this is part of France and part of Switzerland. So the Large Hadron Collider is underneath the ground here, outlined with this yellow line. And this is a giant particle accelerator. It's about 5.5 miles in diameter, I think. And what's buried underground is this tube, and inside of this tube is another tube where particle physics happens. Basically, there are superconductors and a lot of magnetic fields, and they use these to accelerate, in this case, protons at nearly the speed of light. And then they spin them around and around, and then they smash them together. And when they smash them together, you get something that looks like this. This is kind of looking down the barrel of the LHC. And you smash them together, and a whole bunch of stuff happens. All sorts of stuff come out. And they try to pick out from this wreckage interesting things. So in this case, what we see here, this tube is surrounded by a bunch of detectors that can detect anything, neutrinos, photons, electrons, anything that we know about. And so in this case, you could see a couple of jets come out where they've detected a few things. But because we know that energy and momentum are conserved, there's actually stuff that we don't see coming out the bottom here. There's some missing energy there. And so theoretically, they comb through this data, and they try to find something that has some missing energy that looks like a dark matter particle. Now, unfortunately for WIMP dark matter, we haven't seen anything that looks like a WIMP today. But the LHC is being upgraded every day. It's getting more powerful, and we're getting better at combing through the data, the massive amount of data that comes from the LHC. But we still haven't seen anything yet. But stay tuned. So the second thing I'm going to talk about is indirect detection. So this is where a dark matter particle collides with another dark matter particle, and you get some stuff that comes out. So it could be anything. It could be a positron, or it could be light. In this case, if dark matter is a WIMP, if two particles collide, they would create light in the gamma ray part of the spectrum. Okay? And so we can try to look for dark matter using gamma ray telescopes. This is the Fermi telescope, which is a satellite orbiting Earth. And what it does is it takes images of the night sky in gamma rays. And this right here, if you were looking for dark matter, you would want to look at the place where it should be the densest, right? Because that's where you'd get the most collisions. And in the case for us, it would be the center of the Milky Way. So this is a map of the sky, the whole sky, with Fermi in gamma rays. And you can see very clearly the plane of the disk of the Milky Way. It turns out most of this is star stuff that comes from star formation and various gas physics. I don't care about any of that, sorry. But we actually know that stuff extremely well, which is useful for me, so we can get rid of it, okay? And when you get rid of it, in this case, it turns out that there's this, which is a little bit at the very center of the Milky Way that we don't know what it is. So this is called the galactic center excess. And interestingly, it looks suspiciously like what you would expect from a WIMP dark matter particle annihilating two gamma rays. So that's pretty interesting. But unfortunately, we haven't solved it yet because there's some other things that we don't know about. And that's, in this case, pulsars. So this is a pulsar. It's basically a rapidly spinning neutron star. And then they have jets where extreme energies are achieved, and this can actually give off gamma rays as well. And if you have a population, if you assume there's a population of pulsars at the center of the galaxy, it actually looks, unfortunately, a lot like that galactic center excess. So while it's still up for debate, it looks kind of like it's probably just pulsars and not dark matter. So strike number 2. All right, so the last thing that I'm going to talk about is direct detection. And so this is basically utilizing the fact that, kind of the Earth is orbiting the sun, and the sun is kind of moving through our galaxy. And because our galaxy should be in this background of WIMPs, if the dark matter is WIMPs, then there should be kind of this sea of WIMPs that are coming right at Earth. We call this the WIMP wind. It's passing through us all right now. The credit for this is from Symmetry magazine. It's cut in the back. They have all sorts of cutesy little diagrams like this. And so we utilize the fact that we're kind of moving through this bath of WIMPs to try and detect dark matter. And the way that this works is you set up something that's ultra pure and non-reactive, some sort of crystal, maybe made out of some silicon or germanium molecules or something like that, or a liquid noble gas, something that's heavy and non-reactive. So in this case, xenon or argon. And you set up this thing, and you just wait for a dark matter particle to come in. We can't see the dark matter particle. And I said before that dark matter doesn't interact often with normal matter, but it does interact with normal matter. And so hopefully you would see a bump. Basically, it runs into one of these molecules, bumps it a bit, and we can detect what happens when it bumps something. Okay? That's called direct detection. Now, there are several experiments throughout the world that try to do this. I'm going to highlight one. This is the Xenon 1T experiment in Gran Sasso mine in Italy. So this is actually about 1 kilometer under the ground. And so what this is, there's this giant tank on the left here that's filled with water, and this banner here is actually showing what's inside of that tank. And inside of that tank is a smaller tank, and they fill that tank with about 3 tons of liquid xenon. And then they just wait, and wait, and wait, and wait for a dark matter particle to come in and bump something. Now this is, this version has only been running for, I want to say, a year. There have been several other versions that are a little bit smaller. And this is, a great feat of physics. But unfortunately, the big limiting factor is time, right? You have to just wait until something happens. And so I'm going to, kind of wrap up by talking about one kind of somewhat new thing that people have been thinking about to try and eliminate this waiting part. And it's called a Paleo detector. And so what is a Paleo detector? Well, these are Paleo detectors. And you might say, those are rocks. And I would say, they are rocks. Yes, exactly. That's exactly right. But this is kind of just so there are certain crystals that this is better for, but they're basically crystals that are produced in the very early stages of Earth, and they're buried very far beneath the Earth. So they have sort of the effect where they're not sort of impinged on by gamma or anything, cosmic rays or something like that might interfere with this experiment. And so basically what you have is a direct detection experiment that's buried deep underground. So the idea is kind of dig up these rocks and look at them with some sort of electron microscope or X-rays or something like that. And hopefully you see these little streaks. This is from a very old experiment where they're looking at mica for something different. But you would expect tracks in this that look somewhat similar if there was dark matter that basically went into this crystal, bumped something, and created a little borehole through it. Okay? And the size of this would typically be, if it was dark matter, on the scale of a couple nanometers. Okay? No, I forgot to say, but if we're going back here, you might have been you might have known from the fact that I was talking about waiting that we haven't really seen a dark matter particle or a WIMP in this experiment, these types of experiments either. So I'm going to end by talking about the future. Very scary, very scary. So this is a map made by Tim Tate, mapping out some of the the various things that are under the umbrella of dark matter. And I've talked about kind of something over in the weak scale physics over here, one branch of this giant web. And there's all sorts of other stuff, from the controversial and taboo, like MOND, to the interesting and exotic, like, say, primordial black holes or something like this. Each branch of this thing would make a Astronomy on Tap talk of its own, and maybe I'll do that if they convince me to do so. But I think there's a lot of interesting physics going on here, and just because we haven't found a dark matter particle yet doesn't mean, A, that it's not interesting, or B, that it doesn't mean that it's not a WIMP also. So people are going to still be looking for WIMPs, because there's still a lot of really great reasons why it could be a WIMP. But I think in the future, you'll see a lot more modifications to the sort of way we think about dark matter and the assumptions that we make about dark matter and the experiments that try to look for whatever this missing mass is. All right, so I'm going to end there. Thank you all. I'll take any questions.
Awesome. Not a confusing map at all. All right.
Don't think about it that much. The problem is just don't think about it.
Just don't think about dark matter. It's fine. It's just don't worry about it. All right. Questions? Yes, right here in front.
So, if all dark matter were WIMPs, statistically, would we have expected to have found one by now?
Okay. So if dark matter were WIMPs, would we statistically have expected to find one by now? The answer is no, not necessarily. So the thing is, while we have a constraint that the mass of a WIMP should be, we have basically a rough constraint on what the mass and how often it should interact with normal matter is. And we're kind of digging into that region of space. And basically what you could say is if you have some sort of like a direct detection experiment, the longer we go without seeing something, the more you're pushing down like how often it interacts with normal matter space. But there's actually a very large range of masses and interaction probabilities that has not yet been probed by the experiments that I'm talking about. But it is starting to get a little weird, let's say, that we haven't seen it yet.
Starting to get weird? Just now?
Maybe it's already weird.
Okay.
Did I make it weird?
That's what we're good at. All right, right here by the stairs.
Yeah, so for the, I think I heard it, from the Paleo detectors, how do we know it's dark matter and not something else? Is that basically your question? Yeah, okay. Yeah, so basically what I would say is people are still trying to figure that out. So kind of the assumption that they're making is burying it that far underground, something underground that far for that long, it'll be protected from stuff like cosmic rays, which won't make it very far into the surface. But the largest background is basically radioactive stuff around where where this crystal would be buried. And so I think people are still trying to. No one's ever actually dug up anything and tried to do this experiment yet. We're still in the very initial stages of like trying to figure out what material would be best, where best to find it, and then what the backgrounds are. So it's possible. It looks like they are confident that the backgrounds are something that we can deal with. Maybe the tracks would look different or something like that. But we're still trying to figure that out. Excellent question. Thank you.
I can't believe we're in the age of crystals being part of astronomy, but all right,
we're back to it. That was originally what it was like.
We're back to the age. Doesn't bode well. Does anybody up top have a question who I can't see? No, okay, right here.
Is there a possibility that dark matter could carry large structures like real matter does, like galaxies and planets?
Well, oh God. Okay, so yeah. So, dark matter is really kind of even in the WIMP framework, dark matter is really the skeleton on which galaxies are formed. So it has structure in that sense, that gravity kind of drags it into overdensities and underdensities and these sort of streams and stuff like that. But there are other theories of dark matter where it basically what we don't know that well is how does dark matter interact with itself, basically. That's kind of an unknown variable. And so there are theories of what the dark matter does when interacting with itself that maybe tells you that you could get extra structures, it could cool and condense. There's even theories that there's a whole dark universe. Basically, like you have dark atoms, dark electrons, dark protons, and it just doesn't interact with normal matter all that much. So you can imagine people like to make wild claims on like the Discovery Channel that there's a shadow universe that looks just like but
wasn't that a Thor movie?
The Dark World?
Yeah.
Nobody saw it, so nobody knows.
Touche.
Sorry.
No comment. Okay.
Got Thor fans?
No comment. Okay. We do have a Twitter question. So what's the correlation between black holes and dark matter being in the center of galaxies?
Good question, Twitter. So there's a lot of stuff that I could say about this. The answer is, I guess we don't know. So for the black holes, that's the
This
answer.
whole talk is...
Hey, we know some things.
It exists.
Yeah, maybe.
Probably.
But no, but in all seriousness, so black holes, so supermassive black holes, we don't really know what the seeds of a supermassive black hole is. There's some really interesting theories. But they do require, a lot of them do require, much like galaxies do, they require a dark matter halo to sort of be the thing that underpins them, okay? So for the supermassive black holes at the centers of galaxies, they must form we think they must form in a dark matter halo. Okay, so like one way would be a bunch of gas is funneled into a dark matter halo all at once, very early on in the early universe, and it just directly collapses into a giant black hole that then forms the supermassive black holes in galaxies. So that's one thing. Another thing, kind of the opposite, how black holes kind of influence dark matter. So I was talking about direct detections and stuff like that. And because black holes are so massive, they can actually pull dark matter into them. And so you might expect there to be a huge spike in dark matter around black holes. Not within the black hole, because then we wouldn't be able to see anything that comes out of it. But there would be spikes of dark matter around the black hole that could aid in sort of direct detection experiments. So that's how black holes and dark matter kind of relate to one another.